Hello, we are the image processing subteam for the Ponderosa project. My name is Marco Tellez. My team members are Jonathan Arvizu, Angeles Moyotl, and Romina Hernandez. We are working with the Jetson Board TX2 along with the FLIR Blackfly USB 3 camera. The Jetson board runs on an Ubuntu-based operating system. The FLIR Blackfly camera is designed for industry-based machine vision applications. With the use of the camera's FlyCapture SDK and OpenCV, our goal is to deliver data to the controls team, which determines when a wreath enters the field of view, the size and velocity of the wreath. The overall Ponderosa project is a partnership with Boys Republic, a private non-profit school whose focus are troubled youths. Their Della Robbia Wreath program was introduced as a work experience and has become one of their largest fundraisers. We will be automating the painting portion of the program. Here we have a simplified ASM chart of the driver code. On startup, the camera will be calibrated to improve measured values. Once the code detects a wreath entering the field of view, the process to obtain the size is implemented, which would also obtain the velocity. Once the camera detects a new wreath entering, it will send out a flag that will indicate the start of the motors. These blocks will be explained in more detail in the following slides.
Hi, my name is Romina Hernandez, and today I'm going to be talking about our group's initial project design. And so here are the three aspects, the three objectives that we were keeping in mind that we were focusing on as we were creating our code. And these three aspects are supposed to send data out, and so each team member is supposed to work on a different part of the code. And so this first part is the wreath size and velocity, and with that being able to send that data to the motors. Then next, the location of the camera, which would be whether we would keep it within or around the frame. And lastly, to be able to incorporate all our code in the Jetson board, with it being able to read our code, being that our code, we did use Visual Studios just to ensure that every team member could use and write the same code. And so since we no longer had access to BR, we can no longer test the actual wreath. So going on to this next slide, one of the things that we were looking for when we did go in person was where we wanted to place the camera. And so we decided that the camera was no longer going to be attached to a frame. Rather, we would keep it somewhere stationary near the roof to be able to have a good perspective on the reef. And so it was no longer going to move. But as mentioned, since we were going to use a Jetson board, we needed to make sure it ran with FlyCapture, the program that we were using to run in our Visual Studios code. And so this is an area that we were actually having problems with, just to make sure that the code we were creating using FlyCapture, that the Jetson board would actually create. And so this is, like I said, this is an issue that we were looking at because we no longer could, continue to go back to BR and just measure the distance and the size of the actual wreath. We had to use theoretical values for our code to test our code. And so this is something that you're going to see later on.
Hello, I'm Jonathan. I'll be going over camera calibrations with you. To start off with, we were using a FLIR camera to act as our eyes, and we wanted to use OpenCV so we were able to manipulate the information that we are gathering from the camera to what we need it to be. But by default, the FLIR camera comes with its own software called FlyCapture SDK. So to start the process, we need to convert FlyCapture SDK into OpenCV. We needed to do this because the camera lens had a fisheye distortion effect to it. And to fix this, we were to use a chessboard pattern to help calibrate the camera. And once we get the calibration data from the code, we will be able to fix the distortion effects. Moving on to calibration source code, we could see two functions here. The first function is getting the position of the board at any angle, so the camera will be consistently looking for the board. The second function is to look for the corners of the chessboard, like the black squares, so it can track them and get a grid onto it to calibrate it. Looking at the next function, we could see that its purpose is to start the calibration process. It'll go through and take the video feed and calibrate it there currently. The next function, saved camera calibrations. The way that one works is it takes saved pictures from the camera and stores up at least however many the user wants, and from those pictures start calibrating the camera. And if you were to take a look at the next slide that we have here, we can see the code here converting the FlyCapture SDK into OpenCV, then giving the user the choice of what do they want to do once they have the conversion. So we could save a picture of an image that looks good. We could start the calibration once enough images are saved, and we could exit out of it and end the program. And this picture right here is of my colleague here holding up the checkerboard for it to be calibrated by the code.
So as here you can see, this is part of our pixel to distance source code, which, as mentioned in the beginning, we were going to incorporate all our code together in the Jetson board to be able to just have it all run together as one. And so the idea was to condense our code into using this as a function, so that we can use in the overall code. And so the purpose of this function was to give the overall code the pixel to distance information, which we were supposed to determine the size and integrate in our code to determine the size. And this is something that we weren't able to get to, is incorporating the read size, but it's something that we're continuing to work on to be able to also detect the size of the read.
Hello, my name is Angeles Moyotl. I am going to talk about the Jetson board's design process and how we got the Jetson board connected to the camera and Visual Studio. To go about this, we first created a C++ cross-platform project on Visual Studio with an example project from GitHub. Before configuring it with the Jetson board, we ran and debugged it on the Windows platform. Once that was successfully debugged, we managed to add a Linux configuration which connected Visual Studio to the Jetson board. The example bullet standalone was debugged and displayed in the Jetson board as it shows in the image to the left. This bullet standalone project is a CMake project. The advantage of a CMake project is that it can be used as a cross-platform open source tool to build processes that can run on multiple platforms other than Windows. When targeting the Linux machine, we first created and debugged a CMake code on Windows platform, and once that is ran perfectly, we could go to the next thing. When then loaded up and ran the C code on the Jetson board, the sample test code was able to demonstrate that the Jetson board was able to run the CMake C++ project that uses the FLIR camera, the point being that the code is working on the machine. By this, the camera can now be used with our code once finished. The image displayed the code captures and saves the images as PGM files and shows that the images are saving. In conclusion, the Jetson board has been loaded up with the Flight Capture SDK. We established Flight Capture SDK environment on the Jetson board as a process that ensures our code is going to run as it knows the libraries are going to get the SDK working and get the images from the camera, as said in the previous slide. We set up the Jetson board so it could work, but we also set up Visual Studio so that we were able to integrate the Jetson board in there. Once the camera calibration and pixel distance are unfortunately not finished, but we are working on the process of completing it. Well, thank you all